In the outer reaches of the solar system, where sunlight arrives as little more than a distant star's whisper, something ancient drifts through the cosmic dark. The interstellar comet designated 3I Atlas carries within its frozen nucleus the memory of another star system, another time, another place in the galaxy's slow rotation, 4.5 billion years ago, when our sun was still gathering the dust and gas that would become the planets. This wanderer was already old, already travelling, already carrying its cargo of primordial ice through the spaces between stars. The comet measures perhaps 1 kilometre across, though its exact dimensions remain wrapped in the uncertainty that cloaks all visitors from beyond Neptune's orbit. Its surface appears darker than charcoal, blackened by eons of cosmic ray bombardment and the patient chemistry of deep space. Beneath this carbonaceous crust lies a mixture of water ice, frozen carbon monoxide, and methane substances that condensed in the frigid disk around a star whose light went out before Earth learned to breathe oxygen. 3I Atlas moves through the solar system at 17 kilometers per second relative to the Sun, fast enough to escape our star's gravitational embrace entirely once it completes this singular passage. Unlike the familiar comets that return every few years or decades, swept into predictable ellipses by the Sun's pull, this visitor follows a hyperbolic trajectory that will carry it back to the interstellar medium. It has taken roughly 30,000 years to reach us from the heliopause, that distant boundary where the solar wind finally surrenders to the pressure of interstellar space. The comet's journey began in unimaginable cold, drifting through regions where the temperature hovers just a few degrees above absolute zero. For millennia, it travelled through voids where a single hydrogen atom occupies each cubic centimetre of space. Regions so empty that the vacuum between molecules exceeds anything achievable in terrestrial laboratories. Yet even in this near-perfect emptiness, forces were at work. Galactic magnetic fields, weak beyond human comprehension, nevertheless guided the comet's path with infinite patience. The gravitational influence of nearby stars, themselves separated by light years of darkness, created subtle perturbations that accumulated over geological time. As 3I Atlas crossed the heliopause and entered the solar system's sphere of influence, it began to experience pressures unknown during its interstellar wandering. The solar wind, that constant stream of charged particles flowing outward from the Sun at 400 kilometers per second, creates a dynamic pressure that varies with distance and solar activity. Though this wind is tenuous beyond earthly experience, containing fewer particles per cubic centimetre than the best vacuum chambers can achieve, it nevertheless exerts measurable force on objects in its path. The comet, with its irregular shape and slowly rotating nucleus, presents a complex surface to this invisible river of protons and electrons. Scientists studying 3I Atlas have discovered that its nucleus rotates once every 7.5 hours, a leisurely tumble that speaks to countless collisions and gravitational encounters during its journey through interstellar space. This rotation rate places it among the slower spinners of known comets, suggesting either a particularly large size or a structure loosened by thermal cycling over cosmic time. The rotation axis appears tilted with respect to the comet's orbital plane, creating seasons of uneven heating as different hemispheres face the distant Sun. Even at its current distance, well beyond the orbit of Jupiter, the comet has begun to stir. Temperature measurements reveal that its surface, though still colder than liquid nitrogen, has warmed by several degrees since crossing Neptune's orbit. This subtle warming triggers the first whispers of sublimation, the direct transformation of ice into vapour that bypasses the liquid phase entirely. Water molecules, locked in crystalline structures for eons, suddenly find themselves with enough energy to break free from their frozen matrix and drift away into space. The mystery of 3I Atlas deepens when astronomers attempt to determine its exact composition. Unlike solar system comets, whose spectral signatures reveal familiar mixtures of water, carbon dioxide, and organic compounds, this interstellar visitor displays unusual absorption lines that suggest exotic ices formed in different stellar environments. The ratio of heavy water to normal water differs slightly from solar system norms, hinting at nucleosynthesis processes in the progenitor star system that created this wanderer billions of years ago. 3 soft ironies accompany this ancient traveller on its passage through our cosmic neighbourhood. First, despite journeying for 30 millennia to reach us, 3 Atlas will spend less than 2 years within the inner solar system before departing forever, a cosmic blink after an eternity of approach. Second, this messenger from another star system carries chemical signatures that may actually preserve conditions from our own solar system's youth better than any native object. Having been frozen in interstellar space while our local environment evolved and changed. Third, the very forces that will eventually eject this comet from our solar system, gravitational perturbations and radiation pressure, are the same phenomena that originally launched it on its interstellar journey, creating an endless cycle of cosmic wandering. The comet's approach toward the inner solar system follows a trajectory that was determined not by any conscious navigation, but by the accumulated influence of every gravitational field it has encountered during its long journey, the slight tug of the galactic centre, the passage near other star systems, the pressure of interstellar magnetic fields. All these forces have conspired to aim 3I Atlas toward a close encounter with Mars, that rusty beacon of ancient geology and atmospheric loss. As the comet continues its inward fall, gaining speed with each passing day, the forces acting upon it grow more complex and intertwined. The solar wind pressure increases with the inverse square of distance, while thermal effects begin to reshape its surface through the patient work of sublimation and redeposition. Somewhere in the darkness ahead, Mars waits in its 24.5-hour rotation, its thin atmosphere barely thicker than the vacuum of space, yet substantial enough to influence any visitor that ventures too close. The invisible architecture of forces that will guide 3I Atlas past Mars is already beginning to assert itself. Though the comet remains months away from its closest approach, solar photons, each carrying microscopic momentum, strike the comet's dark surface and transfer their energy in the form of gentle but persistent pressure. The comet's irregular shape ensures that this radiation pressure acts unevenly, creating tiny net forces that slowly alter its trajectory in ways that only become apparent over astronomical distances. In the depths of space, patience rules supreme. Forces too weak to move a feather on Earth accumulate over millions of kilometers to nudge comets from their paths, to bend starlight around massive objects, to shape the very architecture of galaxies. 3I Atlas, carrying its cargo of alien ice toward an appointment with the Red Planet, serves as a testament to the quiet persistence of physics operating on cosmic scales, where time is measured not in heartbeats or seasons, but in the slow procession of orbits and the patient decay of radioactive isotopes. The wanderer continues its ancient journey, now caught between the gravitational embrace of our Sun and the magnetic architecture of the solar wind, moving ever closer to a world that has waited 4.5 billion years for this singular encounter. The solar wind flows outward from the Sun's corona like an invisible river that never sleeps, carrying with it the electromagnetic signature of our star's nuclear fusion. At the distance where 3I Atlas currently drifts, this wind has travelled for nearly 2 weeks since leaving the Sun's atmosphere, cooling and expanding as it moves through the vacuum between worlds. Each cubic centimetre of space contains roughly 5 protons and 5 electrons, moving at velocities that would cross the continental United States in less than 20 minutes, yet their combined mass equals less than a grain of sand distributed across a volume the size of a city block. This tenuous stream of charged particles creates what physicists call dynamic pressure, a force that acts on any object in its path like an eternal, gentle breeze, unlike atmospheric wind, which pushes against surfaces through molecular collisions. The solar wind exerts its influence through electromagnetic interactions with the plasma environment surrounding celestial bodies. The comet 3I Atlas, despite its seemingly solid appearance, exists within a complex electromagnetic bubble created by its own outgassing and the interaction of sublimated material with the solar magnetic field. The Sun's magnetic field lines, frozen into the expanding plasma of the solar wind, stretch outward in a spiral pattern created by the star's 25-day rotation. These invisible field lines carve the solar system into sectors of alternating magnetic polarity, creating a structure that resembles the water sprayed from a rotating garden sprinkler. As 3I Atlas moves through this magnetized plasma, it encounters regions where the field lines compress and stretch, creating varying levels of pressure that influence both the comet's trajectory and the behavior of its nascent atmosphere. Scientists monitoring the comet's approach have detected subtle changes in its motion that cannot be explained by gravitational forces alone. The solar wind pressure, though minuscule by terrestrial standards, accumulates over the vast distances of interplanetary space to create measurable deflections in the comet's path. These non-gravitational forces operate with such delicacy that they were not recognized in cometary science until the advent of precise orbital tracking in the late 20th century, when astronomers realized that comets consistently arrived slightly ahead or behind their predicted positions. The mystery of how solar wind pressure translates into orbital changes lies in the complex geometry of electromagnetic interactions around irregular bodies, unlike spherical planets, which present uniform cross-sections to the solar wind. 3I Atlas tumbles through space with an asymmetrical profile that creates varying levels of electromagnetic shadowing. The comet's slow rotation ensures that different regions of its surface experience different durations of solar wind exposure, leading to uneven heating and asymmetrical outgassing patterns that compound the wind's direct effects. Temperature variations across the comet's surface, caused by its irregular shape and rotation, create localized regions where sublimation occurs at different rates. The nucleus resembles a cosmic potato, with deep craters and protruding ridges that cast shadows across neighboring terrain even in the faint sunlight of the outer solar system. These topographical features create microclimates where ice can persist in permanently shadowed regions while exposed areas undergo continuous sublimation, generating jets of gas that interact with the solar wind in complex ways. The comet's dark surface absorbs nearly 90% of the sunlight that reaches it, converting electromagnetic radiation into thermal energy that drives the sublimation process. This absorbed energy heats the subsurface ice layers, causing them to transition directly from solid to gas in a process that requires tremendous amounts of energy per molecule. The escaping gas carries away heat, creating a cooling effect that moderates the surface temperature and establishes thermal equilibrium between incoming solar radiation and outgoing sublimation cooling. As 3I Atlas continues its approach toward the inner solar system, the solar wind pressure it experiences increases according to the inverse square law that governs all radiation from point sources. At its current distance, the wind exerts a force comparable to the weight of a few snowflakes distributed across the comet's entire cross-sectional area. Yet this seemingly negligible pressure operates continuously, without pause. Accumulating momentum changes over millions of kilometers of orbital motion. The interaction between solar wind and cometary material creates what astronomers call a magnetosphere, a region of space dominated by the comet's own magnetic environment rather than the Sun's field lines. Though 3I Atlas lacks the strong intrinsic magnetic field of a planet like Earth, the ionized gases in its developing coma create electrical currents that generate their own weak magnetic fields. These fields interact with the solar wind in ways that deflect some particles around the comet, while allowing others to penetrate deeper into the coma, creating a complex dance of electromagnetic forces. Three gentle ironies accompany the solar wind's patient work on 3I Atlas. First, this wind moves through a vacuum so complete that its individual particles travel millions of kilometers without colliding with each other, yet collectively they create pressure waves that can be measured and predicted. Second, the wind's influence on the comet's trajectory is strongest when the comet is farthest from the Sun, where the absolute force is weakest but competing influences are minimal. Third, The same stellar processes that create the solar wind nuclear fusion in the Sun's core also generated the heavy elements that comprise the comet's rocky components during the death throes of previous generations of stars. The comet's response to solar wind pressure varies with its orientation relative to the flow of charged particles. When the comet's long axis aligns with the wind direction, it presents a smaller cross-sectional area and experiences reduced pressure. When oriented perpendicular to the wind, the comet intercepts more particles and feels stronger deflecting forces. This orientation-dependent pressure creates a subtle torque that gradually changes the comet's rotation rate over astronomical timescales, though the effect is too small to measure during a single orbital passage. Modern spacecraft missions have revealed that the solar wind varies dramatically with solar activity, creating what space physicists call space weather. Solar flares and coronal mass ejections can temporarily increase the wind's density and velocity by orders of magnitude, while periods of solar minimum reduce the particle flux to levels barely above background cosmic radiation. 3i Atlas experiences these variations as subtle changes in the pressure environment, each fluctuation recorded in the precise measurements of its trajectory that ground-based telescopes continuously monitor. The architecture of magnetic field lines in the solar wind creates invisible highways and barriers that channel charged particles along specific paths through the solar system. These field lines connect the Sun's surface to the heliopore's boundary, carrying information about solar conditions to the farthest reaches of the solar system at the speed of light. As 3i Atlas moves through this magnetic web, it encounters regions of enhanced and diminished field strength that modulate the local pressure environment in ways that ripple through the comet's developing atmosphere. The wind continues its patient work, a cosmic sculptor operating on scales of time and distance that dwarf human experience, gradually nudging 3i Atlas along a trajectory that will carry it past Mars and into the inner solar system, where stronger forces await. In the vast emptiness beyond Jupiter's orbit, where sunlight arrives with barely enough energy to warm ice above its sublimation threshold, 3 Atlas begins its slow awakening from the deep freeze of interstellar space. The comet's nucleus, that dark amalgamation of primordial ices and cosmic dust, has remained essentially unchanged for billions of years, preserved in the near absolute zero of the void between stars. Now, as our sun's influence gradually penetrates the comet's ancient structure, molecules that have been locked in crystalline lattices since the formation of distant stellar systems begin to stir with the first whispers of thermal energy. The process begins almost imperceptibly, with individual water molecules gaining just enough kinetic energy to break free from the hydrogen bonds that have held them in place since the comet's birth. These early escapees drift away from the nucleus at velocities measured in meters per second, so slowly that they would take hours to cross a city block. Yet their departure marks the beginning of a transformation that will eventually create an atmosphere around 3i Atlas larger than most planets. A gossamer envelope of gas and dust that extends hundreds of thousands of kilometers into space. The sublimation process follows the ancient physics of phase transitions, governed by the relationship between temperature, pressure, and molecular motion that describes all matter in the universe. At the comet's current distance from the Sun, surface temperatures hover around minus 150 degrees Celsius, cold enough to freeze carbon dioxide into dry ice, yet warm enough to liberate water molecules from their icy prison. The energy required for this transformation, the latent heat of sublimation, equals nearly 10 times the energy needed to melt the same amount of ice, making this direct solid-to-gas transition one of nature's most energy-intensive processes. As 3i Atlas rotates through its 7.5-hour day, different regions of its surface experience varying amounts of solar heating. The comet's irregular shape creates a complex pattern of illumination and shadow, with deep craters remaining perpetually cold, while exposed ridges and plains receive the full, though faint warmth of distant sunlight. This uneven heating drives sublimation at different rates across the surface, creating localized jets of escaping gas that follow the topology of ancient impact craters and tectonic fractures. The escaping gases carry with them microscopic dust particles that have been embedded in the ice matrix for eons. These grains, smaller than particles of flour yet containing the chemical signature of interstellar space, drift away from the nucleus at velocities determined by the balance between gas drag and their own inertia. The largest particles, perhaps a few millimeters across, barely escape the comet's weak gravitational field and eventually fall back to the surface in slow-motion trajectories that take hours to complete. The smallest grains, no larger than smoke particles, ride the escaping gas streams far into space, where they will eventually be swept away by solar radiation pressure. Scientists studying 3I Atlas have identified several distinct gas species in its nascent atmosphere, each sublimating at different temperatures and rates. Water vapor dominates the emission, as expected for a comet formed in the cold outer regions of a stellar system. But spectroscopic analysis also reveals carbon monoxide, methane, and more exotic compounds that hint at the chemical conditions present in the comet's birth environment. The ratio of these gases differs subtly from solar system comets, providing clues about the nucleosynthesis processes that occurred in the comet's progenitor star system billions of years ago. The mystery of why 3I Atlas began outgassing so far from the Sun puzzles astronomers familiar with the behavior of native solar system comets. Typical periodic comets remain inactive until they approach within Jupiter's orbit, where solar heating becomes sufficient to drive significant sublimation. Yet this interstellar visitor shows clear signs of gas emission while still in the outer reaches of the solar system, suggesting either a composition unusually rich in volatile materials or a structure made porous by eons of cosmic ray bombardment and thermal cycling during its interstellar journey. The developing coma, that tenuous atmosphere of gas and dust surrounding the nucleus, remains invisible to the naked eye and barely detectable even with sensitive telescopes. Its density equals roughly 1/10 billionth that of Earth's atmosphere at sea level, so rarefied that individual molecules travel thousands of kilometers before encountering another particle. Yet within this near vacuum, complex chemical and physical processes unfold as solar ultraviolet radiation breaks apart gas molecules, creating ions and radicals that react with each other and with dust grains in ways that mirror the chemistry of interstellar space. The temperature structure within the coma reveals the delicate balance between heating and cooling processes that govern all cometary atmospheres. Gas molecules escaping from the nucleus carry thermal energy that gradually dissipates through collisions and radiation, creating a temperature gradient that drops from perhaps minus 100 degrees Celsius near the surface to the cosmic background temperature of minus 270 degrees at the coma's outer boundary. This thermal structure influences the expansion velocity of the gas, with warmer molecules near the nucleus moving faster than their cooler counterparts in the outer coma. 3 subtle ironies accompany the comet's awakening in the cold depths of the outer solar system. First, the ice that now sublimates into space originally condensed in temperatures even colder than those it currently experiences, formed in the frigid disk around a dying star where thermal equilibrium existed at just a few degrees above absolute zero. Second, the energy driving the sublimation comes from nuclear fusion occurring 93 million kilometers away. Yet the photons carrying this energy left the Sun's core hundreds of thousands of years ago, having spent eons bouncing through the dense stellar interior before beginning their journey to 3I Atlas. Third, the gases now escaping the comet will eventually be swept out of the solar system by the same solar wind that helped guide the comet toward its encounter with Mars, creating a trail of interstellar material that will drift through space long after the comet itself has departed. The sublimation process creates its own micrometeorology around the nucleus, with jets of escaping gas generating pressure waves that propagate through the tenuous coma at the local speed of sound. These acoustic phenomena, though occurring in a medium billions of times thinner than Earth's atmosphere, follow the same physical principles that govern sound transmission in terrestrial environments. The speed of these waves, determined by the temperature and composition of the gas, provides astronomers with a remote sensing technique for measuring conditions within the coma that would otherwise remain unobservable. The comet's rotation introduces a diurnal cycle to the sublimation process, with gas production rates varying as different regions of the surface rotate into and out of sunlight. This creates a breathing pattern in the coma's density, expanding and contracting with the nucleus's rotation period. Ground-based observers detect these variations as periodic changes in the comet's brightness and spectral characteristics, creating a natural clock that reveals details about the nucleus's shape, composition, and thermal properties. As individual molecules escape the gravitational influence of the nucleus, they enter trajectories determined by their initial velocity and the weak but persistent influence of solar radiation pressure. The lightest molecules, hydrogen, created by the photodissociation of water and organic compounds, achieve escape velocities more easily than heavier species, leading to compositional fractionation in the outer regions of the coma. This process gradually enriches the inner coma in heavy molecules while allowing light species to escape preferentially, creating chemical gradients that extend across hundreds of thousands of kilometers. The nascent atmosphere of 3I Atlas serves as a natural laboratory for studying matter under conditions impossible to replicate on Earth, where gas density is intermediate between planetary atmospheres and the vacuum of space interact with electromagnetic radiation and charged particles in ways that reveal fundamental aspects of physics and chemistry. The comet's coma represents a bridge between the solid-state matter of its nucleus and the plasma environment of the solar wind, a transitional realm where molecules, atoms, and ions coexist in delicate equilibrium. The awakening continues, molecule by molecule. As 3 Atlas carries its expanding envelope of ancient gases toward the inner solar system, where the sun's increasing warmth will accelerate the sublimation process and create the spectacular displays that have inspired human observers for millennia. Yet even in its current state, barely active and still months away from its closest approach to the Sun, the comet demonstrates the inexorable influence of stellar radiation operating across the vast distances that separate worlds, gradually transforming ice into atmosphere through the patient application of electromagnetic energy accumulated over cosmic time. The coma of 3I Atlas expands into the darkness like a breath exhaled in cosmic winter, its boundaries invisible yet precisely defined by the balance between outward gas flow and the confining pressure of the solar wind. This tenuous atmosphere, now stretching across distances that dwarf continents, creates its own gravitational and electromagnetic environment distinct from both the solid nucleus at its heart and the vacuum of interplanetary space beyond its edges. Within this gossamer envelope, molecules freed from billions of years of frozen captivity begin their final journey into the void, each following trajectories determined by the subtle interplay of thermal motion, radiation pressure, and the weak magnetic fields that thread through the solar system. The escaping water vapor and carbon monoxide create an invisible shell that catches solar radiation like the most delicate of cosmic sails, converting electromagnetic energy into mechanical force through the momentum transfer that occurs when photons strike gas molecules. This interaction, known as radiation pressure, operates according to principles first described by James Clerk Maxwell in the 19th century, yet its effects on cometary motion remained unrecognized until space-age astronomy provided the precision necessary to detect orbital perturbations measured in meters per second. The force exerted by solar radiation on the coma equals roughly the weight of a paperclip, distributed across an area larger than most countries. Yet this negligible pressure accumulates over astronomical distances to deflect comets from their predicted paths. The coma's response to solar radiation depends critically on the size distribution and optical properties of the dust particles suspended within the gas flow, microscopic grains, their surfaces darkened by eons of cosmic ray bombardment and chemical processing in interstellar space, absorb solar photons across all wavelengths from ultraviolet to infrared. When these particles subsequently re-emit this energy as thermal radiation, They preferentially radiate in directions determined by their temperature distribution and surface properties, creating a net force that can either accelerate or decelerate the comet depending on the particle's rotation rates and thermal characteristics. The physics governing this process involves quantum mechanical interactions between electromagnetic radiation and matter, where individual photons transfer discrete amounts of momentum to atoms and molecules through scattering events that occur trillions of times per second throughout the coma. Each interaction follows conservation laws that have remained unchanged since the first moments after the Big Bang. Yet their collective effect creates macroscopic forces capable of altering the trajectories of kilometre-sized objects moving through space at velocities that would circumnavigate Earth in less than 4 hours. Scientists studying the radiation pressure effects on 3I Atlas must account for the complex three-dimensional structure of the coma, which varies with time as the comet's rotation creates asymmetrical patterns of gas and dust emission. Computer models of this process require solving coupled differential equations that describe fluid flow, radiative transfer, and orbital mechanics simultaneously, incorporating factors ranging from the quantum properties of molecular transitions to the gravitational perturbations caused by distant planets. These calculations reveal that radiation pressure effects on comets operate most efficiently when the particles in the coma achieve an optimal size range large enough to interact strongly with visible light, yet small enough to be easily accelerated by photon impacts. The mystery of precisely predicting radiation pressure effects on individual comets lies in the uncertain nature of their internal structure and composition, properties that remain largely hidden beneath their dark, carbonaceous surfaces. The strength of these non-gravitational forces depends on factors such as the porosity of the nucleus, the distribution of volatile materials within the ice matrix, and the thermal properties that determine how efficiently absorbed solar energy conducts through the comet's interior. Variations in any of these parameters can change the magnitude and direction of radiation pressure forces by factors of 10 or more, making precise orbital predictions challenging even with the most sophisticated computational models. The coma's interaction with solar radiation also generates what astronomers call the anti-tail phenomenon, where dust particles pushed away from the sun by radiation pressure create a faint streak that appears to extend toward our star rather than away from it. This counterintuitive effect results from the orbital mechanics of particles that have been accelerated by radiation pressure, causing them to lag behind the comet in its orbit, and creating geometric configurations where the dust trail appears projected against the sky in directions opposite to the main tail. Ground-based observers of 3I Atlas watch for signs of this anti-tail development, which would confirm that radiation pressure has become strong enough to significantly influence the motion of particles within the coma. 3 delicate ironies characterize the radiation pressure environment around 3I Atlas. First, the same solar energy that created the heavy elements comprising the comet's rocky components through nucleosynthesis in previous generations of stars now provides the photons that will gradually disperse those materials back into interplanetary space. Second, radiation pressure effects are strongest for the smallest dust particles, yet these microscopic grains require the longest time to escape the comet's gravitational influence, creating a size-dependent segregation process that operates over timescales ranging from hours to years. Third, the momentum carried by massless photons, though individually negligible, can cumulatively exceed the gravitational binding energy of loosely consolidated cometary material, demonstrating how quantum mechanical properties of light translate into macroscopic mechanical effects. The expanding coma creates its own optical environment, where scattered sunlight illuminates dust particles in ways that reveal information about their composition and size distribution. Polarization measurements of this scattered light indicate that the particles possess irregular shapes and complex surface textures, consistent with their formation through accretion processes in the turbulent disk around the comet's progenitor star. The wavelength dependence of this scattering follows patterns that suggest mineral compositions similar to carbonaceous chondrite meteorites, those primitive remnants of solar system formation that preserve chemical conditions from the earliest epochs of planetary accretion. As 3 Atlas continues its approach toward Mars, the comet expands at velocities determined by the temperature and composition of the escaping gases, creating a dynamic envelope that grows larger with each passing day. The expansion velocity, typically a few hundred meters per second for water vapor at cometary distances, ensures that molecules released from the nucleus today will occupy regions hundreds of thousands of kilometers in diameter by the time the comet reaches its closest approach to the red planet. This expanding shell of ancient gases will eventually encounter Mars's own magnetic environment, creating interactions between interstellar material and planetary magnetospheres that occur perhaps once per million years for any given world. The radiation pressure acting on 3I Atlas's coma represents just one component of a complex system of forces that will determine the comet's trajectory through the inner solar system, yet its effects will persist long after gravitational influences have diminished, gradually spreading cometary material throughout the solar system in ways that connect the chemistry of distant stars to the evolution of planets and the eventual emergence of life on worlds like Earth. The nucleus of 3I Atlas tumbles through space in a rotation that speaks of countless encounters across galactic distances, its irregular shape creating a complex dance of illumination and shadow as different hemispheres sweep through the faint sunlight of the outer solar system. This 7.5-hour rotation period places the comet among the slower spinners in the population of known comets, suggesting either a particularly large size relative to its observed brightness, or an internal structure loosened by thermal cycling during its multi-billion-year journey through interstellar space. Each complete rotation brings new regions of ancient ice into sunlight, while casting others into the absolute cold of shadow, creating thermal stresses that fracture the surface and generate the asymmetrical outgassing patterns that complicate all attempts to predict the comet's exact trajectory. The comet's spin axis appears tilted with respect to its orbital plane, creating seasonal variations in heating that will become more pronounced as 3I Atlas approaches closer to the Sun. Computer models of this rotation suggest that the nucleus resembles an elongated potato rather than a sphere, with dimensions perhaps twice as long in one direction as another, though the exact ratios remain hidden in the uncertainty that shrouds all measurements of distant, dark objects. This irregular shape ensures that the cross-sectional area presented to solar radiation varies continuously as the comet rotates, creating periodic changes in the amount of energy absorbed and the locations where sublimation occurs most vigorously. The physics of rotation for such an irregular body involves complex interactions between gravitational gradient forces, thermal stresses, and the subtle torques created by asymmetrical outgassing, as jets of escaping gas carry away momentum in directions determined by surface topography and subsurface ice distribution. They create reaction forces that gradually alter the comet's spin rate through processes analogous to those that control the attitude of spacecraft using reaction control systems. These forces operate continuously but imperceptibly, changing rotation periods by fractions of seconds over timescales measured in years, yet their cumulative effects can dramatically alter a comet's orientation over the course of multiple orbital passages. Thermal mapping of the rotating nucleus reveals temperature variations that exceed 100 degrees Celsius between sunlit and shadowed regions, creating expansion and contraction cycles that stress the comet's structure with each rotation period. The dark, carbon-rich surface material absorbs solar energy efficiently, but conducts heat poorly into the interior, creating steep temperature gradients that extend only centimeters below the surface before reaching the deep cold, where primordial ices remain unchanged since the comet's formation. This poor thermal conductivity ensures that seasonal heating effects penetrate only shallow depths, preserving the chemical and isotopic signatures of the comet's birth environment in layers that may never experience temperatures warm enough to drive significant sublimation. The mystery of 3 Atlas's rotation state lies in reconstructing the history of collisions and gravitational encounters that shaped its current spin characteristics during its journey through the galaxy. Computer simulations suggest that interstellar comets experience frequent close approaches to other stars, encounters that can dramatically alter rotation rates through tidal forces and gravitational torques operating over thousands of years. The current rotation period may represent an equilibrium between these ancient perturbations and the more recent effects of outgassing torques, creating a spin state that encodes information about both the comet's interstellar trajectory and its internal structure. Observations of the comet's brightness variations reveal that its rotation creates a complex light curve, with multiple peaks and valleys corresponding to different aspects of the irregular nucleus coming into view. These brightness changes, though subtle, provide the only direct means of determining the rotation period and constraining the shape of an object too distant for direct imaging with current telescopes. Sophisticated photometric analysis of these variations suggests that the nucleus possesses several distinct surface units with different albedos and thermal properties, possibly representing either compositional variations or different degrees of space weathering accumulated during the comet's interstellar travels. The rotation of 3I Atlas generates what astronomers call non-gravitational accelerations through the rocket-like effect of asymmetrical outgassing. When sublimating ice creates jets of escaping gas, the reaction forces can either spin up or spin down the nucleus depending on the geometry of the active regions relative to the rotation axis. These forces, though tiny compared to gravitational influences, accumulate over time to create measurable changes in orbital motion that must be accounted for in precision trajectory calculations. The magnitude and direction of these accelerations depend on factors such as the distribution of volatile materials within the nucleus, the thermal properties of different surface regions, and the complex interplay between rotation state and heating patterns. 3 rotational ironies characterize the motion of 3I Atlas through space. First, the comet's leisurely tumble, slower than Earth's rotation, nevertheless creates centrifugal forces sufficient to eject loosely bound surface materials into space, gradually sculpting the nucleus shape over astronomical timescales. Second, the same irregular shape that makes the rotation complex also maximizes the surface area exposed to solar heating, potentially accelerating the comet's evolution during its passage through the inner solar system. Third, the rotation period that took billions of years to establish through interstellar encounters will likely change measurably during the few months of enhanced outgassing as the comet approaches the Sun, demonstrating how brief periods of activity can undo eons of gradual evolution. The tumbling motion creates its own microenvironment around the nucleus, where escaping gases follow trajectories determined by the combined effects of rotation and thermal expansion. The Coriolis forces generated by the spinning nucleus deflect gas flows in subtle ways that create spiral patterns in the inner coma. Though these effects remain below the detection threshold of current observational techniques, mathematical models of rotating cometary outgassing require solving the equations of fluid mechanics in non-inertial reference frames. Incorporating terms that account for centrifugal and Coriolis accelerations, in addition to the usual pressure gradients and thermal forces that drive gas expansion, the comet's rotation also modulates its interaction with the solar wind. As the changing cross-sectional area presented to the flow of charged particles creates periodic variations in the electromagnetic pressure exerted on the developing coma. During portions of the rotation cycle, when the long axis aligns with the solar wind direction, the comet experiences reduced pressure and enhanced penetration of charged particles into the inner coma. When oriented perpendicular to the wind flow, the nucleus presents a larger obstacle that creates more pronounced electromagnetic shadows and pressure variations. These effects, though subtle, contribute to the complex pattern of forces that will guide 3I Atlas toward its encounter with Mars. The ancient rhythm of rotation continues, marking time in the darkness as it has for eons, each 7.5-hour cycle bringing the comet incrementally closer to the moment when it will sweep past Mars and experience gravitational forces strong enough to measurably alter its trajectory for the first time since leaving its birth star system billions of years ago. Mars grows imperceptibly larger against the star field as 3I Atlas continues its ancient approach, the red planet's gravitational influence extending across millions of kilometers to begin the delicate process of trajectory modification that will define the comet's passage through the inner solar system. At this distance, Mars appears as nothing more than a ruddy point of light, yet its gravitational field operates with mathematical precision according to Newton's inverse square law, creating forces that accumulate over vast distances to produce measurable changes in the comet's velocity. The planet's mass, roughly 11% that of Earth, generates a sphere of influence extending approximately 580,000 kilometers from its center, a region where Martian gravity dominates over solar gravitational gradients in determining the motion of small bodies. The approach trajectory of 3I Atlas toward Mars follows a hyperbolic path determined by the vector sum of the comet's initial velocity and the cumulative gravitational perturbations it has experienced during its journey through the solar system. Computer calculations of this trajectory require accounting for the gravitational influences of all major planets, the pressure effects of solar radiation and solar wind, and the subtle, non-gravitational forces created by asymmetrical outgassing from the comet's nucleus. These calculations reveal that the comet will pass Mars at a distance of approximately 350,000 kilometers, close enough for significant gravitational interaction, yet far enough to avoid tidal disruption or atmospheric capture. The dynamics of the three-body gravitational interaction between Sun, Mars, and comet create what mathematicians call a restricted three-body problem, a system of differential equations that has no general analytical solution, yet can be integrated numerically to arbitrary precision using modern computational techniques. The chaotic nature of such systems means that small uncertainties in initial conditions such as the exact position and velocity of the comet, or the precise timing of outgassing events, can amplify over time to create significant variations in predicted outcomes. This sensitive dependence on initial conditions makes precise long-term trajectory prediction challenging. Even with measurements accurate to fractions of arcseconds from ground-based telescopes, as 3I Atlas enters Mars's extended gravitational environment, it begins to experience tidal forces that arise from the slight difference in gravitational acceleration between the comet's center of mass and its extremities. These differential forces, though utterly negligible compared to the comet's structural strength, nevertheless create subtle stresses that could potentially trigger enhanced outgassing from fractures or weak points in the nuclear structure. The magnitude of tidal acceleration depends on both the distance from Mars and the physical dimensions of the comet, reaching maximum values during the closest approach when gravitational gradients across the nucleus become most pronounced. The gravitational focusing effect of Mars's mass creates what astronomers call a gravity assist or gravitational slingshot, where the comet gains or loses orbital energy depending on the geometry of its approach relative to the planet's motion around the Sun. In the reference frame of Mars, 3I Atlas approaches and departs at the same speed, conserving kinetic energy in accordance with fundamental principles of mechanics. However, in the solar reference frame, the orbital motion of Mars itself contributes additional momentum to the interaction, allowing the comet to gain speed if it passes behind the planet or lose speed if it passes in front, relative to Mars's orbital direction. The mystery of precisely predicting the gravitational deflection lies in the complex coupling between orbital mechanics and the physical processes occurring within the comet itself. Outgassing rates vary with heliocentric distance, rotation state, and seasonal illumination patterns, creating time-dependent non-gravitational forces that influence the trajectory in ways that depend on the detailed thermal and structural properties of the nucleus. These effects, though small compared to gravitational forces during distant encounters, can accumulate over time to create deviations from purely ballistic motion that exceed the precision requirements for accurate predictions. Mars's orbital motion around the Sun at 24 kilometers per second ensures that the gravitational encounter occurs within a dynamically complex environment where multiple reference frames and coordinate transformations must be considered simultaneously. The planet's elliptical orbit creates variations in both its distance from the Sun and its orbital velocity, factors that influence the precise timing and geometry of the encounter with Three Atlas. These orbital elements, determined by observations spanning centuries of telescopic astronomy, provide the foundation for calculating encounter circumstances with accuracies measured in seconds of time and kilometers of distance. Three gravitational subtleties characterize the approaching encounter between Three Atlas and Mars. First, the comet's trajectory will be bent by Martian gravity even before the closest approach occurs, creating a curved path through space that gradually turns the comet's velocity vector toward its eventual post-encounter direction. Second, the gravitational influence extends far beyond the planet's physical radius, with detectable deflections occurring at distances greater than the Earth-Moon separation, demonstrating how mass warps the geometry of space-time across astronomical scales. Third, the energy exchange between comet and planet, though conserved in the total system, redistributes orbital energy in ways that could potentially alter the comet's trajectory sufficiently to affect its subsequent encounters with other solar system bodies over timescales spanning thousands of years. The approach phase represents a transition between the comet's interstellar trajectory, determined by encounters with stars and molecular clouds over galactic timescales, and its brief passage through the inner solar system, where planetary gravitational fields dominate the dynamics. During this transition, Three Atlas experiences forces and accelerations that it has not encountered since departing its birth star system, creating the first significant change in its motion since beginning its journey through interstellar space eons ago. Ground-based observations of the approaching comet reveal subtle changes in its apparent motion against the background stars, shifts measured in milliseconds per day that confirm the gravitational influence of Mars is beginning to alter the trajectory in ways consistent with theoretical predictions. These astrometric measurements, requiring the most precise photographic and electronic detection systems available to modern astronomy, provide real-time confirmation of gravitational theory operating across interplanetary distances on an object that has travelled from beyond the realm of any star's influence. The gravitational environment around Mars includes subtle complexities arising from the planet's slightly oblate shape, its two small moons, and the temporal variations in its mass distribution caused by atmospheric dynamics and seasonal polar cap variations. These higher-order gravitational effects, though vanishingly small compared to the dominant monopole field, nevertheless contribute to the precise trajectory calculations required for understanding how Three Atlas will navigate through the Martian system during its brief but dynamically significant encounter. Mars continues its ancient orbit, carrying its gravitational field through space like an invisible net that will soon capture Three Atlas in a brief gravitational embrace, bending the comet's trajectory and sending it onward toward the inner solar system with a slightly modified velocity that encodes information about this singular encounter between worlds separated by billions of years of cosmic evolution. The dust particles liberated from the nucleus of Three Atlas drift away into space along trajectories that encode the history of their liberation, each microscopic grain following a path determined by its size, composition, and the precise circumstances of its release from the icy matrix that has held it captive since the comet's formation in another stellar system. These particles, ranging in size from molecular clusters containing just a few hundred atoms to aggregates as large as pebbles, spread along the comet's orbital path like seeds scattered by cosmic wind, creating an invisible trail that extends across millions of kilometers of space. The largest grains, their motion dominated by gravitational forces, follow orbits similar to the parent comet, while the smallest particles, more susceptible to radiation pressure, drift outward from the Sun in complex spirals that will eventually carry them to the edge of the solar system. The process of dust liberation begins in the subsurface layers of the comet nucleus, where sublimating ice creates gas pressure sufficient to entrain solid particles and carry them through fractures and pores to the surface. The efficiency of this process depends on the gas flow rate, the particle size distribution, and the cohesive strength of the material binding grains together within the ice matrix. Computer models of this process suggest that only particles smaller than a few millimeters can be effectively lofted by gas drag forces, while larger fragments remain gravitationally bound to the nucleus until mechanical disruption or thermal cycling weakens their attachment to the surface. Once released into space, dust particles immediately begin to experience forces quite different from those that govern their motion within the nucleus. Solar radiation pressure, negligible for the comet as a whole, becomes the dominant influence on particles smaller than a few micrometers in diameter, accelerating them outward from the Sun at rates that can exceed the local gravitational acceleration. This size-dependent force segregation creates a natural sorting mechanism that separates the dust trail into distinct populations based on particle size, with the smallest grains moving fastest away from the comet's immediate vicinity and the largest remaining closest to the original orbital path. The electromagnetic properties of individual dust particles determine their response to solar radiation through complex interactions between incident photons and the quantum mechanical structure of solid matter. Particles composed primarily of silicate minerals, similar to terrestrial sand grains, absorb and scatter sunlight differently than those containing organic compounds or metallic inclusions. The wavelength dependence of these optical properties creates subtle but measurable effects in the scattered light from dust trails, providing astronomers with remote sensing techniques for determining particle composition across interplanetary distances. Theoretical calculations of dust particle trajectories must account for several competing forces that operate simultaneously on different timescales and with varying effectiveness depending on particle properties. Gravitational attraction toward the Sun provides a constant inward acceleration that maintains particles in bound orbits around our star. Solar radiation pressure creates an outward force proportional to the particle's cross-sectional area, but independent of mass, making it most effective on small, low-density grains. The Poynting-Robertson effect, arising from the aberration of solar radiation in the particle's rest frame, creates a subtle drag force that gradually spirals particles inward toward the Sun over timescales ranging from thousands to millions of years. The mystery of precisely tracking dust particle evolution lies in the complex coupling between electromagnetic forces, orbital mechanics, and the poorly understood processes that control particle fragmentation and aggregation in the space environment. Collisions between particles occur rarely in the tenuous density of cometary dust trails, yet when they do occur, the outcome depends critically on particle velocities, compositions, and internal structures that remain largely unknown for interstellar material. Some collisions result in fragmentation that increases the number of small particles, while others may lead to aggregation that creates larger, more gravitationally stable grains. The dust trail of 3I Atlas will eventually become detectable from Earth, using specialized telescopes designed for observing scattered sunlight from interplanetary particles. These observations reveal that cometary dust trails can persist for decades or centuries after the parent comet has departed the inner solar system, creating long-lived signatures of cometary passages that astronomers use to reconstruct the orbital histories of periodic comets. For an interstellar visitor like 3I Atlas, however, the dust trail represents a unique signature that will provide the only long-term observable consequence of its passage through our solar system. 3 dust trail ironies accompany the dispersal of particles from 3I Atlas into interplanetary space. First, the smallest particles that escape most readily from the comet's gravitational influence are also those most likely to be destroyed by solar heating and radiation damage, creating a preferential preservation of larger grains that were initially more difficult to liberate. Second, the radiation pressure that removes dust particles from the comet's vicinity also provides the energy that heats them to temperatures sufficient to alter their mineralogy and surface chemistry, transforming interstellar material into something more closely resembling solar system dust. Third, particles that took billions of years to journey from another star system will be dispersed throughout our solar system in mere centuries, spreading interstellar matter among the planets at rates millions of times faster than their original interstellar transport. The spatial distribution of dust particles along the comet's orbital path creates what astronomers call a syndine synchrone structure, where particles released at the same time synchrones, or with the same radiation pressure sensitivity syndines, form distinct curved patterns in space that can be observed and analysed to determine the timing and physics of dust release events. These patterns, invisible to the naked eye but detectable with sophisticated imaging techniques, provide detailed information about the comet's activity history and the size distribution of particles in its dust trail. As 3I Atlas continues its approach toward Mars, the dust particles it has already released follow slightly different trajectories that depend on when and where they were liberated from the nucleus. This temporal and spatial spreading ensures that the dust trail will not encounter Mars directly, instead passing through regions of space that the red planet occupied days or weeks earlier in its orbital motion. The gravitational influence of Mars on these particles remains minimal due to their small masses and relatively distant approach. Yet future passages of Mars through the dispersed dust trail may create detectable meteor activity in the thin Martian atmosphere. The continuing liberation of dust from 3I Atlas creates an expanding envelope of particles that gradually populates the space around the comet's trajectory with microscopic samples of interstellar material. This ongoing process will intensify as the comet approaches closer to the Sun and sublimation rates increase, eventually creating a visible coma and tail that will make 3I Atlas detectable to amateur astronomers with modest telescopes, transforming an invisible wanderer from interstellar space into a naked-eye spectacle that connects human observers directly to the chemistry and physics of distant stellar systems. The thin atmosphere of Mars, barely 1% the density of Earth's air at sea level, extends far beyond the planet's solid surface in tenuous layers that gradually merge with the vacuum of interplanetary space. This extended atmosphere, composed primarily of carbon dioxide with traces of nitrogen and argon, creates a drag environment that can influence the trajectories of objects passing through the planet's immediate vicinity, though the effect remains negligible for most astronomical bodies due to the extreme tenuosity of the Martian air. As 3I Atlas approaches its closest encounter with the red planet, the outermost fringes of this atmospheric envelope may exert subtle forces on dust particles in the comet's coma, creating interactions between interstellar material and planetary atmospheric processes that occur perhaps once in geological ages. The structure of Mars's atmosphere varies dramatically with altitude, following an exponential decay law that reduces density by factors of 10 for every 20 kilometers of elevation above the surface. At the altitudes where 3I Atlas will pass hundreds of thousands of kilometers above the Martian surface, the atmospheric density approaches that of the best laboratory vacuums achievable on Earth, with perhaps a few dozen molecules per cubic centimeter. Yet even this incredibly tenuous medium possesses enough substance to interact with the most delicate components of the comet's atmosphere through processes that operate on the boundary between fluid mechanics and molecular kinetics. The thermal structure of the upper Martian atmosphere creates temperature variations that range from the frigid cold of space at extreme altitudes to the relatively warmer regions heated by solar ultraviolet radiation and the planet's own thermal emission. These temperature gradients drive atmospheric circulation patterns that extend into the exosphere, creating subtle pressure waves and density variations that propagate upward from the planet's surface. The interaction between these atmospheric motions and the expanding coma of 3I Atlas involves fluid dynamic processes operating in the transition regime between continuum flow and free molecular motion, where traditional aerodynamic equations require modification to account for the discrete nature of molecular interactions. Computer simulations of atmospheric drag on cometary material require solving the Boltzmann equation for gas flow in the rarefied regime, where the mean free path between molecular collisions exceeds the characteristic dimensions of the objects being studied. In this environment, drag forces arise not from pressure differences across surfaces, as in terrestrial aerodynamics, but from the statistical imbalance between molecules striking the leading and trailing surfaces of particles moving through the tenuous gas. The magnitude of these forces depends on the accommodation coefficient that describes how efficiently atmospheric molecules transfer momentum to dust grains during surface collisions. The mystery of quantifying atmospheric drag effects on 3I Atlas lies in the uncertain nature of the interaction between carbon dioxide molecules in the Martian atmosphere and the complex organic and mineral surfaces of cometary dust particles. Laboratory studies of similar interactions under controlled conditions suggest that accommodation coefficients can vary by orders of magnitude depending on surface temperature, composition, and microscopic structure. These variations create uncertainties in drag force calculations that can only be resolved through direct observation of cometary behavior during planetary encounters, making each such event a unique opportunity to test theories of rarefied gas dynamics. The gravitational focusing effect of Mars concentrates atmospheric density along the comet's trajectory in ways that enhance the already minimal drag effects. As 3I Atlas approaches its closest approach point, it passes through regions where the local atmospheric density may be elevated by factors of 2 or 3 compared to the spherically symmetric distribution that would exist in the absence of gravitational focusing. This enhancement occurs because atmospheric molecules, like all matter, experience gravitational acceleration toward Mars, creating a subtle but measurable increase in gas density in the vicinity of the planet's gravitational focus point. The relative velocity between 3I Atlas and the Martian atmosphere creates a hypersonic flow regime, where the comet moves through the tenuous gas at speeds exceeding 20 km per second, far faster than the thermal velocities of atmospheric molecules. In this regime, the interaction resembles molecular beam scattering rather than conventional fluid flow, with atmospheric molecules essentially at rest relative to the high-speed passage of cometary material. The resulting drag forces scale with the square of the relative velocity, making even brief encounters at high speed potentially significant for the smallest dust particles in the comet's coma. 3 atmospheric subtleties characterize the interaction between 3I Atlas and Mars's extended atmosphere. First, the drag forces that might measurably affect microscopic dust particles are completely negligible for the comet's nucleus, creating differential effects that could potentially alter the structure and distribution of material within the coma during the planetary encounter. Second, the atmospheric molecules that interact with cometary material carry isotopic signatures of Martian atmospheric evolution, potentially allowing mass spectrometric analysis of comet-atmosphere interactions to provide information about both objects simultaneously. Third, the energy dissipated through atmospheric drag, though tiny in absolute terms, represents an irreversible conversion of the comet's kinetic energy into thermal motion of atmospheric molecules, creating a minuscule but permanent warming of the Martian atmosphere. The seasonal variations in Martian atmospheric density, driven by the sublimation and condensation of polar carbon dioxide caps, create temporal changes in the drag environment that depend on the timing of 3I Atlas's passage relative to the planet's seasonal cycle. During southern hemisphere spring and summer, when the southern polar cap undergoes rapid sublimation, global atmospheric pressure increases by approximately 20%, enhancing drag effects proportionally. The comet's encounter occurs during northern spring, when atmospheric pressure remains relatively stable, minimizing seasonal variations in the drag environment. The interaction between the comet's coma and Mars's atmosphere also creates the possibility of chemical reactions between interstellar organic compounds and atmospheric constituents. Though the extremely low densities involved make such reactions statistically improbable, if such interactions do occur, they would represent a unique form of interstellar planetary chemistry that could potentially create trace quantities of novel molecular species detectable through sensitive spectroscopic analysis. The products of such reactions, if they exist, would provide direct chemical evidence of the encounter between 3D Atlas and Mars that could persist in the Martian atmosphere long after the comet has departed. The electromagnetic environment around Mars, including the planet's weak magnetic field and the interaction region between the solar wind and Martian atmosphere, creates additional complexities in the comet-atmosphere interaction that go beyond simple mechanical drag effects Charged particles in the comet's coma may follow trajectories influenced by magnetic forces, creating potentially observable auroral phenomena in Mars's upper atmosphere if sufficient quantities of energetic particles penetrate the planet's magnetospheric boundary. These electromagnetic effects, though likely below current detection thresholds, represent another channel through which the passage of 3I Atlas could leave measurable signatures of its encounter with the red planet. The tenuous breath of Mars reaches outward into space, creating an invisible medium through which 3I Atlas will pass during its brief encounter, adding yet another layer of complexity to the gravitational and electromagnetic forces that will shape the comet's trajectory and evolution during this singular meeting between worlds separated by billions of years of cosmic history. The gravitational choreography between Sun, Mars, and 3I Atlas unfolds according to the mathematical precision of celestial mechanics, creating a three-body interaction that transforms the comet's trajectory through space in ways that will echo across cosmic time. This dance of massive objects separated by astronomical distances demonstrates the fundamental interconnectedness of motion in the universe, where every body influences every other body through the invisible threads of gravitational force that extend infinitely through space. The complexity of this interaction emerges from the nonlinear nature of gravitational dynamics, where small changes in initial conditions can amplify over time to produce dramatically different outcomes, making each planetary encounter a unique event whose consequences can reshape an object's cosmic destiny. The mathematical framework describing this interaction requires solving Newton's equations of motion for three bodies under their mutual gravitational attraction, a problem that has challenged mathematicians and astronomers for centuries since its first formulation during the development of classical mechanics. Unlike the elegant analytical solutions that exist for two-body problems, three-body interactions generally require numerical integration techniques that break time into small increments and calculate the evolving positions and velocities of all participants step by step. Modern computational approaches can achieve extraordinary precision in these calculations, predicting positions accurate to kilometers across interplanetary distances and timescales spanning centuries. The restricted three-body approximation, where the comet's mass is assumed negligible compared to the Sun and Mars, simplifies the problem while retaining the essential physics of gravitational perturbation. In this framework, 3I Atlas moves through a gravitational potential field created by the combined masses of the Sun and Mars, following trajectories that curve and twist through space in response to the varying strength and direction of the net gravitational force. The comet's path through this potential landscape resembles the motion of a marble rolling across a curved surface, where hills and valleys correspond to regions of gravitational attraction, and the marble's speed varies according to the local slope. As 3 Atlas approaches Mars, it enters a region of space where the gravitational influence of the red planet becomes comparable to the solar gravitational gradient, creating a transition zone where neither body dominates the dynamics completely. This transition occurs gradually over millions of kilometers, with Martian gravity initially providing only tiny corrections to the comet's heliocentric trajectory, before growing to become the dominant influence during the closest approach phase. The mathematical boundary of Mars's sphere of influence, located approximately 580,000 kilometers from the planet's center, marks the distance where Martian and solar gravitational gradients achieve equal strength for objects on similar orbits. The energy exchange during the gravitational encounter follows conservation laws that have remained unchanged since the formation of the universe, ensuring that the total energy and angular momentum of the Sun-Mars comet system remains constant throughout the interaction. However, this conservation applies only to the complete system. Individual components can gain or lose energy depending on the detailed geometry of their mutual interactions. The comet can acquire additional orbital energy if it passes behind Mars in the planet's orbital motion, effectively stealing momentum from Mars's orbital motion around the Sun, though the energy transfer remains utterly negligible compared to the massive planet's total kinetic energy. The Tisserand parameter, a a mathematical invariant that characterizes orbital motion in three-body systems, provides astronomers with a tool for analyzing how planetary encounters alter cometary trajectories while preserving certain geometric relationships. This parameter, combining orbital elements such as semi-major axis, eccentricity, and inclination into a single quantity that remains approximately constant during gravitational encounters, helps predict the post-encounter orbital characteristics of 3I Atlas based on its approach conditions and the geometry of its interaction with Mars. The mystery of precisely predicting three-body gravitational outcomes lies in the chaotic nature of nonlinear dynamical systems, where infinitesimal uncertainties in initial conditions can grow exponentially over time to create dramatically different evolutionary pathways. This sensitive dependence on initial conditions, first recognized in studies of asteroid motion in the 19th century, means that long-term predictions of cometary trajectories become increasingly uncertain as the prediction timescale extends beyond the characteristic time for chaos to develop for 3 Atlas. Uncertainties in its exact position and velocity at the time of Mars encounter could translate into vastly different trajectories thousands of years in the future. The Hill sphere of Mars, that region of space where the planet's gravitational influence dominates over solar tidal forces, extends approximately 1.2 million kilometers from the planet's center and defines the maximum distance at which Mars could theoretically retain gravitational satellites. Though 3 Atlas will pass well outside this region, the encounter geometry ensures that the comet experiences significant gravitational deflection while remaining on a hyperbolic trajectory relative to Mars. The curvature of this trajectory encodes information about Mars's mass and gravitational constant, allowing the encounter to serve as a natural experiment in gravitational physics across interplanetary distances. 3 gravitational ironies characterize the three-body interaction between Sun, Mars, and 3I Atlas. First, the gravitational forces that will measurably deflect the comet's trajectory operate through completely empty space, demonstrating the action at a distance nature of gravitational interaction that puzzled natural philosophers for centuries before the development of general relativity provided a geometric interpretation of gravity as curved spacetime. Second, the energy exchange between comet and planet, though infinitesimal compared to planetary scales, could potentially alter 3I Atlas's trajectory sufficiently to change its ultimate fate, perhaps determining whether it eventually escapes the solar system or becomes gravitationally bound to the Sun. Third, the mathematical complexity of three-body interactions, which resisted analytical solution for centuries, now yields to computational techniques that can predict outcomes with precision exceeding that of most physical measurements. The gravitational perturbations experienced by 3I Atlas during its encounter with Mars will propagate forward in time to influence every subsequent aspect of its trajectory, creating what mathematicians call sensitive dependence on planetary encounters. Changes in velocity measured in meters per second during the Mars flyby will accumulate over years and decades to produce positional changes measured in astronomical units, demonstrating how brief gravitational interactions can have lasting consequences for orbital evolution. These perturbations ensure that the post-encounter trajectory of 3I Atlas will differ measurably from simple two-body predictions based solely on solar gravitational attraction. The orbital mechanics of the encounter involve complex coordinate transformations between reference frames centered on the Sun, Mars, and the comet itself, each providing different perspectives on the same gravitational interaction. In the heliocentric frame, the encounter appears as a brief perturbation of the comet's solar orbit caused by Mars's gravitational field. In the Mars-centered frame, the interaction resembles a hyperbolic flyby where the comet approaches from infinity, reaches minimum distance, and departs again toward infinity. The comet-centered frame reveals the varying gravitational acceleration experienced throughout the encounter, showing how tidal forces create subtle stresses that could potentially trigger enhanced outgassing or structural changes. The resonance phenomena that govern long-term orbital evolution in planetary systems create the possibility that 3I Atlas's trajectory after the Mars encounter could bring it into gravitational resonance with other planets, particularly Jupiter, whose massive gravitational field dominates the dynamics of the outer solar system. Such resonances, characterized by simple integer ratios between orbital periods, can either stabilize or destabilize trajectories over timescales ranging from centuries to millions of years. The stochastic nature of these interactions means that the ultimate fate of 3I Atlas, whether it escapes the solar system, becomes temporarily bound, or eventually collides with a planet remains fundamentally unpredictable beyond certain probability distributions. The encounter with Mars represents a singular moment in the 4.6 billion year history of both objects, a gravitational handshake between worlds that formed in different stellar systems and have followed vastly different evolutionary pathways through space and time. The mathematical precision with which this interaction unfolds, governed by physical laws discovered through centuries of human scientific endeavour, connects the motion of 3I Atlas to the fundamental structure of space-time itself, demonstrating how local gravitational encounters participate in the grand choreography of cosmic evolution that links the smallest scales of physics to the largest structures in the observable universe. The Yarkovsky effect operates on 3I Atlas with the patience of geological time, converting the asymmetrical absorption and re-emission of solar radiation into tiny but persistent forces that gradually alter the comet's orbit through mechanisms so subtle they remained undetected by astronomers until the advent of precision radar tracking in the late 20th century. This thermal force arises from the temperature lag between the absorption of solar energy and its subsequent re-radiation as thermal infrared photons, creating a net momentum transfer that depends on the rotation rate, thermal properties, and surface characteristics of the comet's nucleus. The effect operates most efficiently on objects whose thermal inertia creates significant temperature differences between their sunlit and shadowed hemispheres, conditions that 3 Atlas satisfies through its slow rotation and dark, thermally insulating surface. The physical mechanism underlying the Yarkovsky effect involves the anisotropic emission of thermal radiation from the comet's surface, where regions that were recently illuminated remain warmer than average, and therefore radiate more intensely in the infrared portion of the electromagnetic spectrum. Since photons carry momentum proportional to their energy divided by the speed of light, this enhanced thermal emission creates a net force that acts like a gentle rocket engine, accelerating the comet in directions determined by its rotation state and thermal characteristics. For a prograde rotator like 3I Atlas, whose spin direction aligns with its orbital motion, the effect typically creates a small but persistent acceleration in the direction of orbital motion, gradually increasing the comet's orbital energy and causing it to spiral outward from the Sun. The magnitude of Yarkovsky acceleration depends on several factors that remain poorly constrained for interstellar objects like 3I Atlas, including the thermal conductivity of surface materials, the heat capacity of subsurface layers, and the efficiency with which absorbed solar energy conducts into the interior before being re-radiated to space. Laboratory studies of meteorite samples and spacecraft observations of asteroids suggest that these thermal properties can vary by orders of magnitude depending on composition, porosity, and the degree of space weathering that accumulates over astronomical timescales. The dark, carbon-rich surface of 3I Atlas likely possesses thermal properties similar to carbonaceous chondrite meteorites, which exhibit relatively low thermal conductivity and significant thermal inertia. Computer models of the Yarkovsky effect on irregular bodies like 3I Atlas require solving complex heat transfer equations that account for the three-dimensional structure of the nucleus, the varying solar illumination created by its rotation and orbital motion, and the wavelength-dependent optical properties that determine how efficiently different surface materials absorb and emit electromagnetic radiation. These calculations reveal that the effect varies significantly with heliocentric distance, reaching maximum efficiency at intermediate distances where solar heating is strong enough to create substantial temperature differences, yet not so intense as to drive rapid sublimation that could overwhelm the thermal force with gas pressure effects. The mystery of precisely quantifying Yarkovsky forces on Thruy Atlas lies in the uncertain relationship between the comet's bulk thermal properties and its response to solar heating during its first passage through the inner solar system. Unlike asteroids and periodic comets, whose thermal characteristics can be inferred from repeated observations over multiple apparitions, interstellar visitors provide only a single opportunity to measure their thermal behavior under solar illumination. The pristine nature of 3I Atlas, preserved in the deep freeze of interstellar space for billions of years, suggests its thermal properties may differ significantly from solar system objects that have undergone repeated thermal cycling during previous encounters with the Sun. The coupling between Yarkovsky forces and orbital mechanics creates feedback loops that can either enhance or diminish the thermal effect over time, depending on how changes in orbital elements alter the comet's distance from the Sun and its exposure to solar radiation. An acceleration that increases orbital energy will gradually move the comet to larger heliocentric distances where solar heating diminishes, reducing the strength of subsequent Yarkovsky acceleration. Conversely, forces that decrease orbital energy move objects closer to the Sun, where enhanced heating can amplify thermal effects, potentially creating runaway scenarios where small initial perturbations grow into substantial orbital changes. The seasonal variation in Yarkovsky acceleration arises from the changing geometry between the comet's spin axis and its orbital motion around the Sun, creating periodic modulations in the direction and magnitude of thermal forces. These variations, which depend on the obliquity of the rotation axis and the eccentricity of the orbit, ensure that the thermal force vector rotates in space over the course of each orbital period, sometimes accelerating the comet and sometimes decelerating it depending on the instantaneous geometric configuration. The time-averaged effect depends on the detailed phase relationships between these variations, making long-term predictions of Yarkovsky evolution sensitive to precise knowledge of rotational and orbital parameters. Three thermal ironies characterize the Yarkovsky effect on 3I Atlas during its passage through the solar system. First, the thermal radiation that creates these orbital perturbations carries away energy that was originally absorbed from the Sun. Yet the momentum transfer associated with this energy loss can actually increase the comet's total orbital energy, demonstrating how momentum and energy conservation operate differently in gravitational systems. Second, the effect operates most efficiently on intermediate-sized objects like 3I Atlas, being too weak to significantly influence large planets, yet too strong to ignore for small particles, placing cometary nuclei in an optimal size range for thermal orbital evolution. Third, the forces that took billions of years to accumulate during the comet's interstellar journey will be overwhelmed by thermal effects operating over mere months during its passage through the inner solar system, illustrating how proximity to stars dramatically accelerates all evolutionary processes. The observational detection of Yarkovsky effects requires precision astrometry that can measure positional changes smaller than the apparent diameter of distant stars, pushing ground-based telescopes to their fundamental limits, imposed by atmospheric turbulence and instrumental stability. Space-based observations, free from atmospheric distortion, can potentially achieve the precision necessary to detect thermal forces on 3I Atlas. Though such measurements require continuous monitoring over months or years to accumulate sufficient signal above the noise level created by other perturbations affecting the comet's motion. The thermal force environment around 3I Atlas becomes increasingly complex as the comet approaches closer to the Sun and sublimation begins to compete with thermal radiation for the energy budget of surface heating. Gas pressure forces from asymmetrical outgassing can either augment or oppose Yarkovsky acceleration, depending on the spatial distribution of volatile materials within the nucleus and the geometry of active regions relative to the rotation axis. The interplay between these thermal and gas pressure effects creates a coupled system where changes in one process influence the efficiency of the other, making theoretical predictions challenging without detailed knowledge of the comet's internal structure. The legacy of Yarkovsky forces on 3I Atlas will persist long after the comet has departed the inner solar system. continuing to operate at reduced efficiency as thermal radiation from the cooling nucleus gradually dissipates the energy absorbed during its solar encounter. These residual effects will slowly modify the comet's trajectory for decades after its departure, creating subtle changes in its ultimate path through interstellar space that depend on the integrated thermal history of its entire passage through our solar system. The moment of closest approach unfolds with the mathematical inevitability of celestial mechanics. As 3I Atlas sweeps past Mars at a predetermined distance that was established billions of years ago by the accumulated gravitational influences the comet experienced during its journey through the galaxy. At precisely 14:23:17, universal time, the comet reaches its minimum separation of 347,892 kilometers from Mars's center, a distance slightly less than that between Earth and its moon, close enough for the red planet's gravitational field to exert maximum influence on the ancient wanderer's trajectory. This singular moment represents the culmination of an encounter that began when 3I Atlas first entered Mars's extended sphere of gravitational influence months earlier, and its conclusion will send the comet onward toward the inner solar system with a measurably altered velocity vector that encodes the signature of this brief but dynamically significant interaction. The geometry of closest approach reveals itself in the precise angular relationships between the comet's velocity vector, Mars's orbital motion, and the gravitational force that connects them across the intervening vacuum. At the moment of minimum separation, 3I Atlas moves relative to Mars at approximately 23 km per second, fast enough to cross the continental United States in less than 4 minutes. Yet the gravitational interaction operates with sufficient strength to deflect this motion by several degrees over the course of hours. The encounter occurs slightly behind Mars in its orbital path around the Sun, creating conditions that transfer a small amount of orbital energy from the planet to the comet through the gravitational slingshot effect that has shaped the evolution of countless small bodies throughout the solar system's history. The tidal forces experienced by 3I Atlas during closest approach reach their maximum of intensity when the differential gravitational acceleration across the comet's nucleus creates internal stresses that, while utterly negligible compared to the structural strength of solid rock and ice, nevertheless represent the strongest non-solar gravitational gradient the comet has experienced since departing its birth star system. These tidal accelerations, measured in fractions of microgravities, arise from the slight difference in Mars's gravitational attraction between the comet's center of mass and its surface features, creating forces that attempt to stretch the nucleus along the line connecting it to Mars while compressing it in perpendicular directions. The relative motion between comet and planet during closest approach creates a dynamic environment where gravitational forces vary continuously in both magnitude and direction, requiring sophisticated mathematical techniques to calculate the precise trajectory modifications that result from this complex interaction. The comet's path curves smoothly through space according to the principles of differential geometry, following what mathematicians call a geodesic in the curved space-time created by Mars's gravitational field. This curvature, though invisible to direct observation, manifests itself in the measurable deflection of the comet's motion that ground-based telescopes can detect through careful astrometric measurements of position changes against the background stars. The encounter velocity during closest approach ensures that the interaction occurs in what dynamicists call the impulsive approximation, where the gravitational deflection happens quickly compared to the orbital timescales of both objects, allowing the trajectory change to be calculated as if it occurred instantaneously at the moment of minimum separation. This mathematical simplification, while not strictly accurate, provides excellent predictions for hyperbolic encounters where the visitor spends relatively little time within the planet's immediate gravitational environment. The actual trajectory modification accumulates gradually over several days as 3I Atlas approaches, passes, and departs from Mars, but the bulk of the deflection occurs during the few hours surrounding closest approach when gravitational forces reach their peak intensity. The mystery of precisely determining the encounter's circumstances lies in the complex interplay between gravitational dynamics and the poorly constrained physical properties of 3I Atlas that influence its motion through non-gravitational forces. Outgassing from the comet's nucleus creates reaction forces that can alter the trajectory in ways that depend on the rotation state, volatile distribution, and thermal properties of the nucleus. Parameters that remain uncertain until direct observation during the encounter provides the first opportunity to measure them. These non-gravitational perturbations, though small compared to the gravitational deflection caused by Mars, can accumulate over time to create measurable differences in the predicted post-encounter trajectory. The electromagnetic environment around Mars during the encounter includes effects from the planet's weak magnetic field, its interaction with the solar wind, and the complex plasma physics that governs the behavior of charged particles in planetary magnetospheres. Though 3I Atlas remains too distant to directly interact with Mars's atmosphere or magnetic field, any charged particles in the comet's developing coma could potentially follow trajectories influenced by electromagnetic forces, creating subtle perturbations that add to the gravitational deflection. These effects, if they exist, would be most pronounced for the smallest dust particles in the coma, which possess the highest charge-to-mass ratios and therefore respond most readily to electromagnetic forces. 3 encounter subtleties characterize the closest approach between 3I Atlas and Mars. First, the moment of minimum separation occurs not when the comet appears closest to Mars as seen from Earth, but when the 3-dimensional distance through space reaches its minimum value, a distinction that can create apparent discrepancies between visual observations and computed encounter geometry. Second, the gravitational force between comet and planet reaches its maximum value at closest approach, yet the rate of trajectory change peaks slightly earlier during the inbound phase when the geometry optimizes the conversion of gravitational attraction into velocity deflection. Third, the encounter occurs too quickly for any significant tidal heating of the comet's interior, yet the brief gravitational stress cycle could potentially trigger enhanced outgassing from pre-existing fractures or weak points in the nuclear structure. The observational coverage of the encounter requires coordinating telescopes around the world to maintain continuous monitoring as Earth's rotation carries different observatories into favourable viewing geometry for 3I Atlas and Mars. This global collaboration ensures that the critical hours surrounding closest approach receive comprehensive documentation from multiple independent observing stations, providing the redundancy necessary to detect subtle effects that might be missed by single-site observations. Space-based telescopes, free from atmospheric distortion and day-night cycles, offer additional opportunities to monitor the encounter with precision unattainable from ground-based facilities. The data collected during closest approach will provide the most accurate measurements of 3I Atlas's mass, size, and physical properties available during its entire passage through the solar system. As the strong gravitational interaction with Mars amplifies small effects that would otherwise remain undetectable, the precise timing of trajectory deflection, combined with theoretical models of gravitational dynamics, allows astronomers to constrain the comet's mass and internal structure in ways that purely photometric observations cannot achieve. These measurements will inform understanding of the physical properties of interstellar material and provide ground truth for theoretical models of comet formation in other stellar systems. The encounter concludes as gradually as it began, with 3I Atlas receding from Mars along a hyperbolic trajectory that carries it inexorably toward the inner solar system, where the sun's increasing warmth will drive ever more vigorous sublimation and create the spectacular displays that transform invisible wanderers into objects of wonder and scientific fascination. The gravitational signature of Mars, encoded in the comet's modified velocity vector, will influence every subsequent aspect of its trajectory, connecting this brief encounter to the comet's ultimate fate in ways that demonstrate the fundamental interconnectedness of motion in gravitational systems. The magnetic fields threading through the space around Mars weave invisible patterns that guide the motion of charged particles according to principles of electromagnetic physics that operate on scales ranging from atomic to planetary, creating a complex environment where the interplanetary magnetic field carried by the solar wind interacts with Mars's own weak magnetosphere in ways that subtly influence the passage of 3I Atlas and its developing coma, unlike Earth's strong dipolar magnetic field, which creates a well-defined magnetospheric cavity that deflects the solar wind around our planet. Mars possesses only remnant magnetic fields concentrated in localized crustal anomalies that generate a patchy, irregular magnetosphere extending just a few thousand kilometers above the planet's surface. These fossil magnetic signatures, preserved from an ancient epoch when Mars may have possessed a global magnetic field generated by a convective dynamo in its molten core, now serve as the only barriers protecting the thin Martian atmosphere from direct interaction with the solar wind. The interplanetary magnetic field, frozen into the expanding plasma of the solar wind according to the principles of magnetohydrodynamics, arrives at Mars carrying the magnetic signature of solar activity that originated in the Sun's convective zone and was carried outward by the flow of charged particles at velocities approaching 400 kilometers per second. This field, though weak by terrestrial standards with strengths measured in nanotesla, nevertheless exerts measurable forces on any electrically charged material it encounters, including the ionized gases and charged dust particles that comprise the outer regions of cometary comas. The field lines form complex patterns that spiral outward from the Sun due to the star's rotation, creating a magnetic web that connects all objects in the solar system to the electromagnetic environment of our central star. As 3 Atlas approaches Mars, its nascent coma enters regions where magnetic field lines have been distorted by their interaction with the red planet's tenuous atmosphere and localized crustal magnetic fields, creating a complex electromagnetic environment where particles can become trapped, accelerated, or deflected depending on their charge state and initial velocity. The process of ionization, driven by solar ultraviolet radiation and collisions with energetic particles, gradually converts some fraction of the neutral gas molecules in the comet's atmosphere into charged ions and free electrons that respond to electromagnetic forces, in addition to the gravitational and pressure forces that govern the motion of the neutral material. The magnetic field topology around Mars during the encounter includes features such as magnetic reconnection regions, where oppositely directed field lines merge and release stored magnetic energy, current sheets where the field direction changes rapidly over short distances, and magnetic islands where field lines close on themselves to create isolated regions of trapped plasma. These structures, though invisible to optical observation, create distinct environments where the charge components of 3I Atlas's coma could potentially undergo acceleration, heating, or deflection that would distinguish them from the bulk motion of neutral particles following purely ballistic trajectories under gravitational influence. Computer simulations of charged particle motion in planetary magnetospheres require solving the equations of motion for individual particles moving under the combined influence of electromagnetic forces, gravitational attraction, and collisions with neutral atmospheric constituents. These calculations reveal complex trajectories that can include cyclotron motion around magnetic field lines, bounce motion between regions of high magnetic field strength, and drift motion across field lines due to gradients in field strength or curvature. The characteristic timescales for these motions range from microseconds for electron-cyclotron periods to hours for large-scale drift motions, creating a hierarchy of electromagnetic effects that operate simultaneously on different spatial and temporal scales. The mystery of electromagnetic interactions between 3I Atlas and Mars lies in the uncertain degree of ionization within the comet's coma and the unknown charge distribution on dust particles that have been exposed to interstellar cosmic rays for billions of years. Laboratory studies suggest that cosmic ray bombardment can create surface charges on insulating materials that persist for long periods in the vacuum of space, potentially giving interstellar dust grains net electrical charges that would make them responsive to magnetic forces. However, the sign, magnitude, and distribution of such charges remain poorly constrained for objects that have travelled through environments quite different from the solar system's radiation environment. The interaction between the comet's ionized atmosphere and Mars's magnetic field could potentially create detectable auroral phenomena in the thin Martian atmosphere if sufficient quantities of energetic charged particles penetrate the planet's magnetospheric boundary and follow field lines down to atmospheric levels where they could collide with carbon dioxide and nitrogen molecules. Such auroral emissions, if they occur, would appear as faint glows in ultraviolet and visible wavelengths that space-based telescopes could potentially detect during the hours surrounding closest approach. The intensity and spatial distribution of any auroral activity would provide direct evidence of electromagnetic coupling between the interstellar visitor and Mars's magnetic environment. 3 magnetic subtleties characterize the electromagnetic environment during the encounter between 3I Atlas and Mars. First, the magnetic fields that guide charged particle motion operate through forces that are always perpendicular to both the field direction and the particle velocity, creating curved trajectories that conserve kinetic energy while dramatically altering direction, demonstrating the fundamental difference between electromagnetic and gravitational interactions. Second, the strength of magnetic forces on charged particles increases with particle velocity, making the electromagnetic effects most pronounced for the fastest moving ions in the comet's expanding coma, while gravitational forces remain independent of velocity and therefore dominate the motion of slower, neutral material. Third, magnetic field lines act as invisible conduits that can transport charged particles across vast distances without significant energy loss, potentially connecting the comet's coma to Mars's upper atmosphere through electromagnetic pathways that bypass the usual barriers imposed by gravitational and pressure forces. The solar wind interaction with Mars during the comet's passage creates time-variable magnetic field conditions that depend on the instantaneous state of solar activity and the orientation of the interplanetary magnetic field relative to Mars's orbital motion. Coronal mass ejections, solar flares, and the rotation of magnetic field sectors past Mars all contribute to a dynamic electromagnetic environment that changes on timescales ranging from minutes to days. These variations ensure that the magnetic field configuration experienced by 3I Atlas during its encounter represents a unique snapshot of solar planetary electromagnetic interactions that may never be exactly repeated. The electromagnetic signature of the encounter, encoded in the subtle deflections of charged particles within the comet's coma, will propagate outward with the expanding atmosphere to create a record of the interaction that persists long after 3I Atlas has departed from Mars's immediate vicinity. This electromagnetic memory, carried by ions and charged dust grains following trajectories modified by their brief interaction with planetary magnetic fields, provides a mechanism for information transfer between astronomical objects that operates in addition to the gravitational and photonic channels that dominate most astronomical phenomena. The magnetic whispers that guide charged particles through the space around Mars operate according to physical laws that connect the quantum mechanical properties of individual electrons and ions to the large-scale structure of planetary magnetospheres, demonstrating how electromagnetic phenomena link atomic physics to astronomical dynamics across the vast range of scales that characterize the universe. These invisible forces, though weak compared to gravity on astronomical scales, nevertheless play crucial roles in shaping the evolution of planetary atmospheres, the propagation of cosmic rays, and the complex plasma physics that governs the space environment throughout the solar system. The departure of 3I Atlas from Mars's gravitational embrace unfolds with the same mathematical precision that governed its approach, as the comet recedes along a hyperbolic trajectory that carries it inexorably toward the inner solar system, with a velocity vector now permanently modified by its brief but dynamically significant encounter with the red planet. The gravitational slingshot effect has imparted additional orbital energy to the ancient wanderer, accelerating it by approximately 3 kilometers per second relative to its pre-encounter velocity, a small change by terrestrial standards yet sufficient to alter the comet's trajectory in ways that will influence every subsequent aspect of its passage through our solar system and its eventual return to interstellar space. The receding comet carries with it the invisible signatures of its Martian encounter, encoded in the precise deflection angles that characterize its post-flyby trajectory. Angles that ground-based telescopes can measure with unprecedented precision thanks to the dramatic amplification of small gravitational effects that occurs during close planetary approaches. These trajectory modifications follow the principles of orbital mechanics with such exactitude that they provide astronomers with a natural experiment in gravitational physics, where the theoretical predictions of celestial mechanics can be tested against the observed motion of an object whose previous trajectory was determined by 4 billion years of galactic dynamics rather than solar system forces. As 3I Atlas moves away from Mars, the various forces that acted upon it during the encounter begin to diminish according to their different distance dependencies, with gravitational forces falling off as the inverse square of separation distance, while electromagnetic and atmospheric effects decrease even more rapidly due to their stronger distance dependence. This gradual transition from planetary to heliocentric dynamics creates a complex force environment where the comet simultaneously experiences the weakening influence of Mars and the strengthening effect of solar radiation pressure as it approaches closer to the Sun, leading to trajectory modifications that reflect the interplay between multiple physical processes operating on different scales. The thermal environment around the departing comet continues to evolve as solar heating increases with decreasing heliocentric distance, driving enhanced sublimation rates that create ever larger quantities of gas and dust in the expanding coma. This increased outgassing generates stronger non-gravitational forces through the rocket effect of asymmetrical gas emission, forces that begin to compete with the gravitational deflection caused by Mars in determining the comet's precise trajectory. The coupling between thermal effects and orbital dynamics ensures that the legacy of the Martian encounter becomes intimately connected to the comet's physical evolution, as it transforms from a nearly inactive nucleus to an object displaying the spectacular coma and tail phenomena that characterize active comets. The expanding dust trail left by 3I Atlas as it recedes from Mars creates a tenuous cloud of interstellar particles that will remain in the vicinity of the red planet's orbit for decades or centuries, gradually dispersing under the influence of solar radiation pressure and gravitational perturbations from other planets. This debris field, though invisible to direct observation due to its extremely low density, represents a permanent alteration to the local dust environment around Mars that could potentially be detected by sensitive space-based instruments capable of measuring the scattering of sunlight from microscopic particles. Future spacecraft missions to Mars might encounter individual dust grains from 3I Atlas, providing the first direct samples of interstellar material ever collected in the vicinity of another planet. The mystery of the comet's post-encounter evolution lies in predicting how the enhanced solar heating it will experience during its continued inward journey will interact with structural changes potentially triggered by tidal stresses during the Mars flyby. Gravitational encounters can sometimes activate previously dormant regions of cometary nuclei by opening fractures or exposing subsurface ice layers to solar heating for the first time in billions of years. If such activation occurs, it could dramatically alter the comet's brightness and outgassing patterns in ways that would be detectable from Earth, but difficult to predict based solely on pre-encounter observations. The velocity increment imparted to 3I Atlas by its gravitational interaction with Mars will propagate forward in time to influence every subsequent phase of the comet's trajectory, creating changes in arrival times at future waypoints that accumulate according to the principles of orbital mechanics. These timing changes, initially measured in minutes or hours, will grow to days or weeks by the time the comet reaches its closest approach to the Sun, and to years or decades by the time it eventually departs the solar system. This amplification of encounter effects over cosmic timescales demonstrates how brief gravitational interactions can have consequences that persist far beyond the duration of the original encounter. Three departure ironies characterize the receding trajectory of 3I Atlas as it leaves Mars behind. First, the comet's increased velocity toward the Sun, gained through its interaction with Mars, will actually cause it to spend less time in the inner solar system where solar heating is most intense, potentially reducing the total amount of mass it loses to sublimation during its passage through our cosmic neighbourhood. Second, the gravitational energy gained from Mars represents borrowed orbital energy from the red planet's motion around the Sun. Yet this energy transfer is so small compared to Mars's total orbital energy that it would take trillions of similar encounters to measurably alter the planet's orbit. Third, the comet now carries information about Mars's mass and gravitational field encoded in its modified trajectory, making it a messenger that could, in principle, convey details about the red planet's physical properties to observers in other star systems billions of years in the future. The electromagnetic environment around the departing comet gradually simplifies as it moves away from Mars's complex magnetosphere and returns to the more uniform conditions of interplanetary space, where the solar wind and interplanetary magnetic field create relatively predictable conditions for the transport of charged particles. The ionized components of the comet's atmosphere, which may have experienced deflection or acceleration during their passage through Mars's magnetic environment, now follow trajectories determined primarily by solar radiation pressure and the general expansion of the coma under gas pressure forces. The observational challenges of tracking 3I Atlas during its departure phase include the increasing angular separation between Comet and Mars as seen from Earth, which gradually reduces the precision with which their relative positions can be measured and makes it more difficult to detect subtle trajectory modifications caused by the encounter. Ground-based telescopes must now track the comet against the stellar background without the benefit of Mars as a nearby reference point, requiring absolute astrometry techniques that are more challenging than the relative position measurements possible during the approach and closest encounter phases. The legacy of the Mars encounter will remain encoded in every aspect of 3I Atlas's future motion, creating a permanent connection between this interstellar visitor and the red planet that will persist throughout the comet's subsequent journey through our solar system and its eventual return to the depths of interstellar space. This gravitational memory, inscribed in the mathematical language of orbital elements and velocity vectors, ensures that the brief interaction between these two ancient objects will continue to influence the comet's cosmic destiny, long after both have travelled far from the location where their paths crossed in the darkness of space. The departure continues, each passing hour carrying 3I Atlas farther from Mars yet closer to the Sun, where increasing warmth awaits to transform the dark wanderer into a spectacular display of sublimating ice and liberated dust, creating the visible manifestations of cometary activity that have inspired human wonder and scientific curiosity throughout recorded history. The various forces that guided 3I Atlas during its encounter with Mars gradually diminish as the comet recedes into the inner solar system. Their influence is weakening according to the mathematical laws that govern interactions across astronomical distances, yet their cumulative effects remain permanently encoded in the trajectory modifications that will shape every subsequent aspect of the comet's cosmic journey. The solar wind pressure, which created subtle but persistent forces during the comet's approach to Mars, continues to operate with slowly increasing strength as 3I Atlas moves closer to the Sun and enters regions where the density and velocity of charged particles streaming from our star create measurably stronger dynamic pressure on the expanding coma and its entrained dust particles. The electromagnetic forces that may have influenced charged components of the comet's atmosphere during its passage through Mars's magnetosphere now fade to negligible levels as 3I Atlas moves beyond the reach of planetary magnetic fields and returns to the relatively uniform electromagnetic environment of interplanetary space. Here, the interplanetary magnetic field carried by the solar wind provides the dominant electromagnetic influence, creating conditions that guide the motion of ions and charged dust grains according to principles of plasma physics that operate throughout the heliosphere. These electromagnetic effects, though individually small, collectively influence the evolution of the comet's coma in ways that become increasingly important as sublimation rates increase with continued solar heating. The gravitational environment around the departing comet transitions from the complex three-body dynamics that characterized its interaction with Mars to the simpler two-body problem of motion under solar gravitational attraction, modified by the growing influence of non-gravitational forces created by asymmetrical outgassing from the nucleus. This transition occurs gradually over millions of kilometers as Mars's gravitational influence weakens according to the inverse square law, creating an extended region where both solar and planetary forces contribute to the net acceleration experienced by 3I Atlas. The mathematical complexity of this transition zone requires numerical integration techniques to achieve the precision necessary for accurate trajectory predictions. The thermal forces acting on 3I Atlas continue to strengthen as the comet approaches closer to the Sun, with both the Yarkovsky effect and radiation pressure increasing according to their respective dependencies on solar flux and temperature gradients within the nucleus. These thermal effects, which were barely detectable during the comet's sojourn in the outer solar system, now begin to create measurable trajectory perturbations that accumulate over time to produce orbital changes comparable in magnitude to those caused by gravitational encounters with planets. The asymmetrical heating of the irregular nucleus creates temperature patterns that drive preferential thermal emission in directions determined by the comet's rotation state and surface topography, generating net forces that act like tiny rocket engines operating continuously as long as solar energy creates sufficient temperature gradients within the nucleus structure. The radiation pressure environment around 3I Atlas evolves as the strengthening solar flux creates increasingly powerful momentum transfer from photons striking gas molecules and dust particles in the expanding coma. This electromagnetic pressure, operating through the same physical principles that power solar sails and cause comet tails to point away from the Sun, creates forces that scale with the inverse square of heliocentric distance and therefore strengthen rapidly as the comet continues its inward journey. The effectiveness of radiation pressure depends critically on the optical properties of cometary material, with dark, absorbing particles experiencing different acceleration than bright, reflective grains of similar size and composition. The outgassing forces generated by sublimating ice create an increasingly dominant component of the non-gravitational acceleration experienced by 3I Atlas as rising temperatures drive enhanced production rates of water vapor, carbon dioxide, and other volatile species. These gas pressure forces operate through the rocket principle, where the momentum carried away by escaping molecules creates reaction forces that can significantly alter the comet's trajectory if the outgassing occurs preferentially from one hemisphere or is concentrated in discrete jets aligned with surface features. The magnitude and direction of these forces depend on factors such as the distribution of volatile materials within the nucleus, the thermal properties that control how efficiently absorbed solar energy reaches subsurface ice deposits, and the complex fluid dynamics that govern gas flow through fractures and pores in the nuclear structure. The mystery of predicting the relative importance of different force components lies in the uncertain physical properties of an interstellar object that has spent billions of years in an environment quite different from the solar system's radiation and particle environment. The pristine composition of 3I Atlas, preserved in the deep freeze of interstellar space, may respond to solar heating in ways that differ significantly from the well-studied behavior of periodic comets that have undergone multiple passages through the inner solar system. Laboratory studies of interstellar dust analogues and telescopic observations of other interstellar visitors provide some guidance. Yet each such object represents a unique sample of material formed under different conditions in distant stellar systems. The coupled evolution of thermal, electromagnetic, and outgassing forces creates a complex feedback system where changes in one type of force influence the effectiveness of others in ways that can either amplify or diminish the total non-gravitational acceleration. Enhanced outgassing increases the density of gas and dust in the coma, which affects both radiation pressure and electromagnetic interactions with the solar wind. Changes in rotation state caused by outgassing torques alter the thermal patterns that drive Yarkovsky forces. These coupling effects make long-term trajectory predictions challenging, even with sophisticated computer models that attempt to account for all relevant physical processes. The observational detection of diminishing force effects requires precision astrometry that can measure positional changes smaller than the resolution limits of most ground-based telescopes. Pushing observational techniques to their fundamental limits imposed by atmospheric turbulence, instrumental stability, and the finite photon flux available from distant astronomical objects, space-based observations, free from atmospheric distortion, offer improved precision but remain limited by the relatively small apertures of existing space telescopes and the long integration times required to achieve sufficient signal-to-noise ratios for astrometric measurements accurate to millisecond levels. Three-force diminishment subtleties characterize the evolving dynamics of 3I Atlas as it recedes from Mars. First, the forces that become weaker with increasing distance from Mars are simultaneously joined by other forces that strengthen with decreasing distance from the Sun, creating a complex transition where the dominant influences on the comet's motion change gradually rather than abruptly. Second, the time delays inherent in thermal processes mean that the thermal forces responding to solar heating continue to evolve for days or weeks after the incident flux changes, creating lag effects that complicate the relationship between heliocentric distance and thermal acceleration. Third, the cumulative nature of small force effects means that perturbations which seem negligible over short timescales can produce substantial trajectory changes when integrated over the months or years of the comet's passage through the inner solar system. The mathematical framework for analyzing the diminishing influence of encounter-related forces involves solving systems of coupled differential equations that describe the time evolution of orbital elements under the combined influence of gravitational and non-gravitational perturbations. These equations, derived from the fundamental principles of celestial mechanics and thermodynamics, require numerical integration techniques that can maintain accuracy over the long timescales necessary to follow the comet's complete trajectory through the solar system. The solutions reveal how initial conditions established during the Mars encounter propagate forward in time to influence the comet's motion throughout its subsequent journey. The transition from encounter-dominated to thermal-dominated dynamics marks a fundamental change in the character of forces acting on 3I Atlas, shifting from interactions that depend primarily on the gravitational and electromagnetic properties of planetary environments to processes that reflect the intrinsic physical and chemical properties of the comet itself. This transition connects the comet's brief interaction with Mars to its longer-term evolution as a sublimating body responding to solar heating, demonstrating how astronomical encounters can trigger or modify physical processes that continue to operate long after the original interaction has ended. The legacy of force interactions during the Mars encounter will remain detectable in the precise trajectory of 3I Atlas for years or decades into the future, creating opportunities for astronomers to use the comet's motion as a probe of fundamental physics operating under conditions that cannot be replicated in terrestrial laboratories. The comet serves as a natural experiment in the complex interplay between gravitational, thermal, electromagnetic, and gas pressure forces operating across the vast range of scales that characterize astronomical phenomena. From the quantum mechanics of photon-matter interactions to the large-scale dynamics of orbital motion around stars, the ancient paths of interstellar space welcome 3I Atlas back into their embrace as the comet continues its outward journey beyond Mars, carrying with it the accumulated influences of its brief but transformative passage through the complex force environment of our solar system, where gravitational, thermal, electromagnetic, and pressure effects have combined to alter its trajectory in ways both subtle and profound. The vast emptiness that stretches between the stars operates according to different physical principles than the dynamic environment near planets and their moons, returning the comet to a realm where particle densities approach the theoretical limits of vacuum and where the nearest sources of significant gravitational influence lie light years away among the distant stars of the galactic neighborhood. The interstellar medium that awaits 3I Atlas beyond the heliopore's boundary consists of gas and dust so tenuous that individual atoms and molecules can travel for years without encountering another particle. Yet this near-perfect vacuum nevertheless possesses structure and dynamics that influence the motion of objects passing through it over timescales measured in millions of years. The local interstellar cloud through which our solar system currently moves contains approximately 1 atom per cubic centimetre, predominantly hydrogen with traces of heavier elements, along with microscopic dust grains that serve as condensation nuclei for the formation of more complex molecular species in the cold depths between stellar systems. The magnetic field structure of the interstellar medium creates invisible pathways that guide the motion of charged particles according to the principles of magnetohydrodynamics, operating on scales that dwarf even the vast dimensions of planetary magnetospheres and creating galactic-scale patterns in the distribution of cosmic rays, interstellar gas, and magnetic flux that connect individual star systems to the broader electromagnetic environment of the Milky Way galaxy. These fields, though weak by terrestrial standards with strengths measured in microgauss, nevertheless exert measurable forces on charged particles over the enormous distances and timescales characteristic of interstellar travel. The gravitational environment of interstellar space reflects the collective influence of hundreds of billions of stars distributed throughout the galactic disk, creating a smooth potential field that guides stellar orbits around the galactic center, while producing subtle perturbations that can alter the trajectories of small bodies over cosmological timescales. The nearest stars to our solar system, located several light-years away, contribute gravitational forces that are utterly negligible compared to solar system dynamics, yet become significant when integrated over the millions of years required for interstellar passage between neighboring stellar systems. As 3I Atlas eventually crosses the heliopause and returns to truly interstellar conditions, it will experience a dramatic change in its particle environment, as the solar wind pressure that has influenced its motion throughout its passage through our solar system gives way to the quite different conditions of the interstellar plasma. This transition, occurring gradually over several astronomical units, as solar wind pressure weakens and interstellar pressure strengthens, marks the boundary between heliospheric and galactic physics, where fundamentally different processes govern the interaction between small bodies and their surrounding medium. The thermal environment of deep interstellar space approaches the cosmic microwave background temperature of 7 Kelvin, so cold that virtually all chemical processes cease and physical evolution proceeds primarily through nuclear decay, cosmic ray bombardment, and the extremely slow diffusion of energy through solid materials. At these temperatures, 3I Atlas will return to the dormant state it maintained during its billions-year journey to reach our solar system, with its surface cooling to equilibrium with the cosmic background radiation, while its interior retains trace amounts of thermal energy absorbed during its passage through the inner solar system. The mystery of the comet's ultimate fate during its return to interstellar space involves predicting how the structural and compositional changes it experienced during solar heating will affect its long-term evolution in the cold and radiation environment between stars. The thermal cycling that occurred during its passage through our solar system may have created fractures, altered surface chemistry, or modified internal structure in ways that could influence how the comet responds to future encounters with other stellar systems over the course of galactic orbital motion. These changes, though subtle, could potentially alter the comet's trajectory when it eventually encounters the gravitational influence of other stars during its continued journey through the galaxy. The cosmic ray environment of interstellar space subjects 3I Atlas to continuous bombardment by high-energy particles accelerated in supernova explosions, stellar winds, and other violent astrophysical processes, creating slow but steady changes in surface chemistry and internal structure through nuclear reactions that occur at rates determined by the flux and energy spectrum of galactic cosmic rays. This space weathering process, operating over timescales of millions or billions of years, gradually darkens surfaces, creates complex organic molecules, and generates trace quantities of rare isotopes that serve as chronometers for measuring the duration of interstellar exposure. 3 interstellar subtleties characterize the environment that awaits 3I Atlas during its return journey to the realm between stars. First, the apparent emptiness of interstellar space actually contains structure and dynamics that operate on scales vastly larger than those familiar from solar system astronomy, with density variations, magnetic field patterns, and shock waves that span hundreds of light years and influence stellar formation and evolution throughout entire galactic spiral arms. Second, the timescales characteristic of interstellar processes dwarf even geological time on Earth, with typical crossing times between stellar systems measured in millions of years and complete galactic orbital periods requiring several 100 million years, placing interstellar dynamics in a temporal regime where stellar evolution becomes a significant factor in environmental change. Third, the near-collision-free environment of interstellar space allows small bodies like comets to preserve chemical and isotopic signatures from their formation environments for billions of years, making them time capsules that carry information about stellar nucleosynthesis and planetary formation processes from ancient epochs in galactic history. The departure of 3I Atlas from our solar system will occur with the same inexorable precision that governed its arrival, as gravitational dynamics and conservation laws determine a hyperbolic escape trajectory that will carry the comet beyond the gravitational influence of the Sun and back into the galactic environment from which it came. The velocity vector that results from its passage through our cosmic neighborhood, modified by planetary encounters and thermal forces, will determine the comet's path through the local stellar neighborhood for millions of years, potentially bringing it within the gravitational sphere of influence of other star systems where it might experience similar encounters with different planetary configurations. The scientific legacy of 3I Atlas's passage through our solar system will persist long after the comet itself has vanished into the darkness between stars, providing astronomers with detailed measurements of interstellar material properties, interplanetary dynamics, and the complex physics of small body interactions with stellar radiation and planetary gravitational fields. These observations will inform theoretical models of comet formation and evolution, while providing ground truth for understanding how interstellar visitors can serve as messengers that carry information about distant stellar systems to observers throughout the galaxy. The silence of deep space gradually reclaims 3I Atlas as it continues its ancient journey, returning it to the timeless realm where individual lifetimes shrink to insignificance compared to the patient cycles of stellar birth and death that govern evolution on galactic scales, where the chemical elements forged in supernova explosions slowly mix and redistribute to provide the raw materials for future generations of stars and planets, and where the vast distances between worlds ensure that encounters like its brief passage through our solar system represent rare and precious opportunities for scientific discovery and cosmic connection across the fundamental loneliness of space. The vast emptiness settles back into its patient rhythm as 3I Atlas disappears into the darkness between worlds, carrying with it the invisible signatures of forces that shaped its trajectory during a brief but remarkable encounter with the gravitational architecture of our solar system. The comet recedes beyond the reach of even the most powerful telescopes, becoming once again a wanderer among the stars, its motion now permanently altered by pressures and perturbations that operated with mathematical precision across distances measured in astronomical units and timescales spanning months of careful orbital evolution. The forces that guided this ancient visitor through its passage near Mars' solar wind pressure, thermal radiation effects, electromagnetic interactions, and gravitational dynamics continue their patient work throughout the solar system, shaping the motion of countless other objects in ways both subtle and profound. These same physical principles operate across the universe, from the quantum interactions between photons and atoms to the large-scale dynamics of galaxies rotating through space, connecting the brief encounter between 3I Atlas and Mars to the fundamental laws that govern matter and energy throughout the cosmos. In the silence that follows departure, the mathematical beauty of celestial mechanics reveals itself through the precision with which gravitational forces bend space and time to guide the motion of objects across interplanetary distances, demonstrating how the geometry of space-time itself participates in the ancient dance between worlds. The trajectory modifications encoded in the comet's velocity vector will propagate forward through time, influencing its path among the stars for millions of years, creating connections between this moment and cosmic futures that stretch beyond human imagination. The invisible pressures that steered 3I Atlas near Mars return to their eternal work, operating with the same patient persistence that has shaped planetary systems since the formation of the first stars, waiting with infinite patience for the next wanderer from interstellar space to enter their domain and experience the gentle but inexorable forces that connect all matter in the universe through the fundamental interactions of physics operating across cosmic distances and timescales. Sleep settles over the ancient paths between worlds, where gravity and light continue their timeless conversation in the language of mathematics, and where the patient forces of nature wait to guide future visitors through the quiet architecture of space. Each encounter a unique moment in the vast symphony of cosmic motion that connects every grain of dust to every distant star.